Students, welcome back again. In this lecture session, we are going to see some channel transitions in open channel flow. So transition would mean there is a change in cross-section or something, the slope of the channel. So changing of a channel flow condition occurs when it changes from one form to another due to the following reasons. The first one, changing cross-section or the width of the channel. Sometimes widths may increase or decrease, or change in the bed slope of the channel. There may be abrupt change in elevation of the channel and change in alignment. Sometimes the alignment of the channel may be changed or shifted, maybe curved or something cornered, and change in the channel shape also. If the channel shape is changing, so there is a transition. So there is some form of energy will be changed, maybe from subcritical to supercritical or subcritical to critical flow. Now let us see the detail now. Let us see channel with a hump. If there is a step which is sometimes upward step or downward step, what will happen? So the concept of specific energy and critical depths are extremely useful for the analysis of problems connected with transitions. So to illustrate the various aspects of such hydraulic parameters, a few simple transitions in rectangular channels are presented here. Let us see if there is subcritical flow, what will happen. Let us see, this is a channel which is horizontal bed. If you have upward step with delta Z height, then you have upstream depths Y1 and specific energy E1 you have. So E1 is Y1 plus V1 square over 2G. This is the general equation. Then we will check whether subcritical or supercritical flow here in the upstream of the hump. Then sometimes a drop in water surface elevation, then it may reach YC, critical depths over the hump, and Y2 you have, then E2 you have, then delta Z you have. So I think second, just specific energy in the second section at this point, you have Y2 plus V2 square over 2G. So assume frictionless surface, then Y2 plus Q square over 2G B square Y2 square. So for upward step, you have E2, which is E2 is above this step. You have E1 minus del Z. So E1 is above this surface. Then if you subtract del Z, you have upward step. But for downward step, you will just increase this one. So you have to add del Z for downward step. So you have upward step and downward step equations. We will follow these formulas. So drop in water surface, which is del Ws, which is drop in water surface, Y2 minus del Z minus Y1. Since Y1 is the upstream depth and del Z is the step, which is upward step, then if you decrease, then you can have drop in water surface elevation. So sometimes it can drop or increase. Then let us see this picture presentation, which is just you have, for example, E1, which is upstream specific energy, and then you have del Z, which is step, which is hump step height. Then E2 you have. Then you can see now from P to P prime, which is just subcritical and supercritical flow, we will see, and R1. So when you go, Q is constant, discharge is constant through the channel, then you will have some change and you can go to this side. Then you have to reach up to YC. So if del Z is increasing or decreasing, what will happen? So if the step height is increasing, then you have to see critical depths will reach. So the critical depths at downstream phase will just will make. So let us see now for supercritical flow. For supercritical flow, if Y1 is in supercritical flow region, then this shows that the depth of flow should increase. So it will just go, there's just jump will be formed due to the reduction of specific energy. Is the reduction of specific energy. In Fig 2.110, point P prime corresponds to y1. Corresponds to y1. Let us go back again. This point P, which is at this point, corresponds to y1, which is this one. It will just correspond to this one. You can see. So P is corresponds to y1, which is upstream. Then what will happen? Then and point R prime to depths at section 2, which is R, just R prime is at section 2. So up to the critical depths, y2, just up to the critical depths, y2 increases. Y2 increases to reach yc. To reach yc at del z is equal to del z max. So del z is equal to del z max. At del z max will be, it will reach at this point. So from R up to this point. So you are just going from y2 at R point, at this point, R, then it will reach up to this if del z is increasing or if the stepwise is increasing. When del z is equal to del z max, y will reach to critical depths. Y will reach to critical depths. So we have to follow this for supercritical flow. So the depths over the hump, y2 is equal to y1 will remain constant. Will remain constant when del z is just reaching up to maximum, and the upstream depths y1 will change automatically. It will change. It will just decrease to have higher specific energy, which is E1 prime. So the new depths will be calculated by iteration. So the variation of depths y1 and y2 with del z in supercritical flow is shown in the figure 2.2. So you can see in figure 2.11 for subcritical flow, just for subcritical flow, a drop in elevation of water surface is just existing. Then if you have del z, if you go to del z, if del z is just increasing, then it will reach yc. So there is a drop in water surface elevation. Otherwise, over the hump, it may just increase. So this is just constant y1. Then if you increase del z up to maximum, above maximum, then the depths will increase. This is variation of y1 and y2 in subcritical flow, flow over the hump. But variation of y1 and y2 on supercritical flow over a hump is just there is a rise in water surface elevation. When you go, the del z just increasing, then it will just y2 will increase, then yc will drop. If you go above del z max, then y1 will drop automatically. So there is a drop in water surface elevation if you go up to maximum. So then let us see the second, portion, transition with a change in width. If the width of the channel is changing, what will happen? For subcritical flow, which is fluid number less than 1, just at the upstream phase, consider a frictionless horizontal channel with width B1 carrying a discharge Q constant at a depth Y1, just as in figure 2.14 here. This is figure B1 here. You have B2. Then there is reduction in width of the channel. But as upstream phase, you have E1, Y1 plus B1 square over 2G is equal to Y1 plus, in terms of Q, you have this. So energy line you have, Y1 you have, then E1. Then if there is a decrease in the channel cross section, then at section 2, just Y2 will drop, then you may reach up to YC. Transition with width constriction will happen. So E2 is this one. Then what will happen? So at section 2, the channel width has been constricted to B2. So from B1, it will be reduced to B2 by a smooth transition. By a smooth transition, something bell mouse, something curved. Since there are no losses involved, and since the bed elevations at section 1 and 2 are the same, the bed elevation is the same. So at both sections, they are the same. So the specific energy at section 1 is equal to the specific energy at section 2. So specific energy at section 1 and specific energy at section 2 will be equal. So we will just use this equation for iteration purpose. We will use accordingly. In terms of discharge, you can use this one, and E2 this one. Then let us see the sketch. So let us see this sketch. So you have drop in water surface elevation. This is energy line. Then it will reach up to critical depths. What will happen if the width of the channel, the second width, is reduced below the minimum, just the minimum width is available? What will happen? Let us see. It is convenient to analyze the flow in terms of discharge intensity. So discharge intensity is given by this equation, Q over B. Then at section 1, Q1 is equal to Q over B1, Q over B1. And at section 2, Q over B2. So since B2 is less than B1, then Q2 will be more than Q1. Since the width is constricted, then let us see just subcritical flow above this line and supercritical. So just if you have E1 first, this one is specific energy at section 1 with width B1. Then at point B, you have Y1 depths. Then this point, you can go to this point, then up to this point. If there is a change in width, then specific energy will be changed. So just it will go Q1 you have, then Q2 is greater than Q1, then you can find any point, then Y2 will be at this point, and critical depth is at this point. So the minimum specific energy that will attain with width constriction. And in the specific energy diagram, in this figure, just drawn with the discharge intensity as a third parameter point. Discharge intensity as a third parameter, we can compare maximum Q for E1 prime, you can, for this one, maximum will be this point. And for this one, you can find at this point again. So when specific energy is increasing, then the depth will be changed. We can calculate. Okay, P on the curve Q1. P on the curve Q1. P is this one on the curve Q1. Then corresponds to depth Y1 and specific energy E1. Since at section 2, E2 is equal to E1, which is from the previous equation, and Q is equal to Q2. Point P will move vertically downward to point R. Point P, this point P will go to point R. To point R, which is this one, this point. So from Q1 to Q2, Q2 is larger than Q1, then downward to point R on the curve Q2 to reach depth Y2. So it will reach to depth Y2 from Y1 to Y2. So if Q is changing, so since Q2 is larger than Q1, then let us see this. In subcritical flow, the depth Y2 is less than Y1. In subcritical flow, the depth Y2 is less than Y1. If B2 is made smaller, if B2, the width in section 2 is made smaller, then Q2 will increase. Q2 will increase according to the previous equation, and Y2 will decrease. Y2 will decrease. If Q2 is increasing, then if B2 is made smaller, then Y2 will decrease. Automatically, the depth at section 2 will decline. So the limit of contracted width B2 is equal to B2 minimum. The minimum width to attain critical flow is obviously reached when corresponding to E1. So the discharge intensity Q2 is equal to Q2 minimum. That is the maximum discharge intensity for a given specific energy or critical flow condition will prevail at section 1. So at this minimum width, just Y2 will reach critical depth at section 2, which is YCM. Then E1 is equal to ECM, the critical, the minimum specific energy, then YCM. Then you can just convert into discharge, Q over area, which is instead of velocity. Then finally, we can have for rectangular channel at critical flow YC, or specific energy is 3 over 2 of YC, or YC is 2/3 of EC. Then by substitution, E1 is equal to ECM. Then finally, just after substitution, YC is Q square over B2 square G, the whole 1/3. Then rearranging this equation, so the minimum width will be this equation to attain critical flow at section 2. So this is the minimum width at section 2, square root of 27 Q square over 8G A1Q. If B2 is made very small, very less than the minimum width, the discharge intensity Q2 will be larger. Again, Q2 will be larger because Q is capital Q over B. Then if B is decreasing, then definitely sure the specific discharge is increasing, larger than the maximum discharge intensity consistent with E1. So the flow will not occur. Therefore, be possible with a given upstream condition. So you can rearrange the upstream conditions. So there is also enlargements and constrictions in a channel width. If you have decrease in a channel, as usual, we can see how the water surface elevation is changing. If you have YC here, then you can have a contracted channel. This is a contracted channel. B is water level in contracted channel, which is this one. From Y1, it will drop to Y2 in contracted channel. And just a specific energy diagram for a contracted channel is this one, specific energy diagram. And this is water surface level or water level in contracted channel, which is supercritical flow. Okay, the other topic is momentum principle. So according to Newton's second law of motion, the change in momentum, which is dmv per unit time, is equal to the resultant of all external forces acting on a body. So in our case, a body of water flow in a channel in our case. So body of water, just body of water as a fluid mass will be considered. So net force summation of force is equal to dmv by dt. So the application of Newton's second law in one-dimensional flow to the controlled volume, that is equating the sum of all external forces to the rate of change of momentum for any two cross sections 1 and 2 gives this equation. So net force, summation of all forces is equal to rho Q, then V2 minus V1, change in velocity. So density of the fluid times flow rate, then change in velocity between the two sections. So you have, this is just static and dynamic force associated with a flow. You can see this is just a diagram which is static forces gamma W y square, because you have here y depths. This is y depths. Then at the base you have gamma times y. So if you calculate the area of this cross section, it is triangular distribution 1/2 gamma W times y square. So this is the equation for static force. But dynamic force, which is rho Q times the velocity of the flow coming to this side. And total momentum will be dynamic force plus static force. This is the total momentum. So momentum function is y square over 2 plus q square over gy. So this is an important issue in momentum principle. So the net force is equal to rho q, change in velocity between 1 and 2, then, or including the momentum correction factor, beta 2, beta 1, you can include. This is 1, and this is also 1. Then, momentum correction factor is given by this equation. Summation of I starts from 1 up to n, vi square times ai. So the area of any cross-section summation. You have to multiply then average velocity square times summation of area. Then if you rearrange this equation, the force which is exerting can be computed. So force on the gate, you can apply Solus gate. If force of friction, which is divided by rho g, is equal to A1 Y1 bar plus beta 1 Q square over G A1 minus A2 Y2 plus beta 2 Q square G times A2. So momentum before and momentum after. So A is the cross-sectional area and Y bar is the depth of center of gravity of the cross-sectional area, and which is the depth of the centroid of the cross-sectional area measured below the water surface. And FF is the total friction force acting along the surface of the body. So this is momentum depth diagram. You can see momentum depth diagram. So this is momentum at depth. So we have discharge intensity just at this point, at this point, at this point, we can see Y1, which is this one, depth, with this discharge, which is with 10 discharge, you can see at this point, but with this discharge, 30, if discharge is increasing, you can see the depth is also increasing, etc. You can see this is the momentum diagram, MY diagram. So thanks for watching. I hope if you have any question, you are welcome.